Now, just a quick reconstruction of the picture from the preceding. We have some angle theta naught, and we're going to have a vector r of 0 at that theta naught. The vector is going to be at angle theta naught with the polar axis, and r naught is going to point out to the position of the reference point at the t equals 0 time, because theta naught corresponds to the angle when theta is 0. V of 0 in 2 dimensions is going to be this green vector. A of 0 is going to be this vector, so that our projections on the x-axis give us the position x of 0, and also give us, projecting the v vector down here, we get the vector which I'll call vx of 0. And I'm not going to draw it because it would just clutter the picture up, but it's clear that we can also project the a of 0 down on the x-axis, and we'll get ax of 0. Angular velocity will be taken to be omega, and that's going to be constant. So that at time t, we will have gone through some angle omega t, giving us our new r vector. This will be our vector r of t. And we'll have a velocity vector, v of t, and an acceleration vector, a of t. Each with its projection onto the x-axis. As before, I'll go ahead and project the x vector. So here's our new position. This will be our position x of t. And our velocity v of t will be the projection of this vector onto the x-axis. So that'll be what we'll call vx of t. So at the initial point, we have this position and motion in this direction represented by this vector, and the magnitude of that vector represents how fast the object is moving. And similarly over here, at time t, we have the position, the velocity, and we would have the acceleration. I chose not to include it in the sketch. So as the point moves around the circle, these three vectors follow it, and their projection gives you the position, velocity, and acceleration of the point undergoing simple harmonic motion on the x-axis. From theta naught and the radius of the circle, which is a, the amplitude of motion, haven't written that down, and omega, we get the function r of t, and it's very straightforward. The angle of r of t, which would be this angle here, that's the angle of r of t with the positive x-axis, is just theta naught plus omega t. So r of t is at angle theta naught plus omega t, has magnitude of a. It follows then that r of t is equal to this function. Okay, a times the cosine of theta, a times the cosine of the angle being omega t plus theta naught, and a times the sine of the angle being again omega t plus theta naught. The cosine in the I direction, the sine in the j direction. The vectors, velocity and acceleration vectors for the motion in 2 dimensions follow. I just have etceteras down here. V of t equals etc. You take the derivative of the r of t function, or you can note that the magnitude of the velocity is r omega, or a omega in this case, And you can derive it either way, that this is 90 degrees ahead of this one and has magnitude omega A. The acceleration is at 90 degrees ahead of that one and has magnitude omega squared A, just the magnitude of a radial acceleration. So you really want this picture. You really want to understand this picture. It's the picture that defines simple harmonic motion.